This is the third episode in the series, All You Need to Know About Stars. Links to part 1 and part 2 will be in the description below. Stars are giant spheres of hydrogen and helium which are massive enough for nuclear fusion to ignite in their cores. The energy produced by nuclear fusion causes the star to expand, while gravity causes the star to contract. And when these two forces are in balance, the star is in a state of equilibrium. Now, let's talk about nuclear fusion. In the cores of stars, hydrogen is in a state known as plasma, which means that electrons are stripped away from their protons due to extreme heat. Nuclear fusion is a process where two lighter nuclei merge together to form one heavier nucleus. For example, two hydrogen nuclei merging together into one helium nucleus. In stellar cores, nuclear fusion happens in a process known as the proton-proton chain. The chain begins when two protons crash at extreme speeds, fast enough to overcome the electromagnetic repulsion between them, causing one of the protons to release its charge in the form of a positron, and the proton converts into a neutron. The positron, being an antimatter particle, annihilates one of the electrons in the surrounding, releasing energy in the form of two gamma rays. Then, the hydrogen nucleus fuses with another hydrogen nucleus that does not have a neutron, fusing together to make helium-3. This reaction also releases energy in the form of a gamma ray. Helium-3 is not as stable as helium-4, which is the final product of the proton-proton chain. Helium-4 is formed when two helium-3 nuclei fuse together to form one helium-4 nucleus, releasing two protons in the process. Here is the full proton-proton chain. Firstly, two hydrogen nuclei fuse. One of them loses its charge in the form of a positron, and then they fuse with another hydrogen nucleus to make helium-3. Then this helium-3 nucleus fuses with another one to form helium-4, releasing two protons in the process. And the energy produced in the form of gamma rays through nuclear fusion is eventually released from the star, in the form of visible light, infrared light, and UV rays. The energy produced by nuclear fusion heats up the star, and hot gas expands. However, gravity causes the star to contract, and when the expansion force and the contraction force are equal, the star is in a state of equilibrium. Since light is a form of electromagnetic radiation, it can travel through a vacuum, which is how sunlight is able to reach the Earth and the other planets. Stars consist of mainly hydrogen and helium. For example, the Sun consists of around 73.5% hydrogen, 25% helium, and 1.5% metals. Note that, in astronomy, metals are any elements else than hydrogen or helium. The concentration of metals in a star is known as metallicity. A common measurement of stellar metallicity is the concentration of iron divided by the concentration of hydrogen. After that, the concentration of iron over the concentration of hydrogen in the Sun is subtracted from this value. Iron over hydrogen metallicity is measured on a scale known as DEX, which is logarithmic, meaning that if a star's metallicity is 0 DEX, it has the same metallicity as the Sun. If a star's metallicity is positive 1 DEX, it has 10 times the metallicity of the Sun. If a star's metallicity is negative 1 DEX, it has 10 times less metallicity than the Sun, and so on. Some stars have a higher metallicity than the Sun, for example, Sirius A, with a metallicity of around positive 0.5. Some stars have an exceptionally low metallicity, for example, HD 122563, with a metallicity of around negative 2.75. The outermost layer of a star is known as the photosphere. Spots of reduced temperature and brightness sometimes form on the photospheres of stars. On the Sun, these are called sunspots. Sunspots can last anywhere from a few days to up to several months, before they disappear. they can get really large. Some sunspots grow to a diameter of around 100,000 kilometers or bigger. Some of them grow even larger. The leading theory about their formation is that they are caused by magnetic fields forming inside of the sun's convection zone, which limit energy transfer to the photosphere, causing dark spots to appear on it. Above the sun's photosphere, there is a layer of plasma extending for millions of kilometers. It is known as the sun's corona, which can be seen during a total solar eclipse. The sun's corona is much hotter than the photosphere. Its temperature exceeds 1 million degrees Celsius. Solar flares occur when accelerated particles interact with plasma, leading to magnetic reconnection causing them to be violently ejected. Magnetic reconnection occurs when a magnetic field interacts with plasma, rearranging it and causing particle acceleration. Another form of solar activity is known as a coronal mass ejection, or CME, which occurs when magnetic fields generated under the sun's photosphere rise above the photosphere, releasing huge amounts of energy and plasma. The sun's magnetic field goes through what is known as the solar cycle, which is a cycle that takes 11 years to complete once. It involves changes in the sun's magnetic field and solar activity. The sun's activity increases at solar maximum and decreases at solar minimum. Now, let's talk about another stellar phenomenon known as stellar wind. Stellar wind is a continuous flow of matter being ejected from the upper atmosphere of a star. Astronomers believe that large stars such as red giants emit more stellar wind, while hot, massive stars such as B and O type stars emit stellar wind at faster speeds. Stellar wind ejected by the sun is known as solar wind, and when it interacts with the Earth's magnetic field, it leads to phenomena such as auroras. And we've reached the end of the video. Bye, see you next time.